All right, welcome back. This is Chapter 10 continued, and this time it is Section 10.2. So please watch the 10.1 video first. But in Section 10.2, we talk about something called arithmetic series. And an arithmetic series is constrained to a very special type of list. It's a list with a starting value and, well, they all have a starting value, and we're adding the same thing every time. I'm writing plus D here. We're adding D every time. We call D the common difference, and so you add D every time. Now, I just have both things up here. Well, eventually I have a bunch of things up here, but sometimes we describe this list of numbers, well, I can think it's kind of obvious, as a list. Sometimes it just says, here's the list, and they want you to do something with the list. Other times they might start the problem with just this little bit right here. They'll give you A, which remember from before is the first term, and then they'll give you D. Now, if they give you D, you know it's an arithmetic series because by definition, the letter D is the letter we're adding to change the term. Now, if you're with me on the previous video, not every series is based on addition. This one was not based on addition. I didn't add the same thing every time, so this was not a geometric, or sorry, it was not an arithmetic series. But anyhow, this one is. So one of the answers might be, tell me what A is and what D is. I kind of think of like when you're talking about a circle, sometimes the answer is the formula. Sometimes the answer is the graph. Sometimes the answer is just what's R and what's the center. So a lot of different ways you can answer a question. So what are we describing when we have this list? Well, the list itself, A and D. We could play the game we were playing back in 10.1 where you tried to figure out the formula. And if you remember that, we're looking for a formula that consistently works for all these numbers. When you put in a 5, you get -5. When you put in a 4, you get -2. And we could try to, leave this up to our imagination to come up with the formula. The good news is we don't have to. And that's why I say this section is a lot more structured than the previous one. All right. So in this section, we have this formula. To find the formula, it is A sub n equals A, which is the first term, plus n minus 1d. So in other words, I could do this whether I have the list or not. I could find this. I could just substitute into this formula. Let me put both these on the window here. All right. I have A and I have D. So if I know what A is, I can just plug that in. If I know what D is, I can just plug that in and calculate. I distributed the -3, and I get -3n plus 10. Let's see, that's the formula that would give me a 7 when I put in a 1, a 4 when I put in a 2, a 3 when I put in a 1, or rather when I put in a 3. So that's I got the formula, and I just got the formula by substitution rather than trying to, what I call imagination, rather than trying to figure out what the list was. All right. So again, this is the formula for arithmetic sequences. D means we're adding the same thing every time. It's negative in this case, but we're adding the same thing every time. And A is the starting value, and we can just substitute it and plug it in. So pretty nice formula to know. All right, what's the next thing they might ask us to do? I can't see the problem from here. All right, I'll write it here. What if they asked us what 7 plus 4 plus 1 plus -2, or just -2, plus -5 or -5 is? All right, of course, I can just add these up, but we have a formula that allows us to add up any number of terms in an arithmetic sequence. So if I wanted to add these up using our formulas, we have one. It's the sum of the first n terms of an arithmetic sequence. And it is, well, it comes in different forms. This is the form I'm used to writing in. And when I say it comes in different forms, sometimes I put the n out in front, or sometimes I'll change the order, but it always works out to be exactly like this. And a1 plus an. All right, so just so you know, we're looking for a number when we're looking for the sum of the first n terms. So everything here is a number. This isn't a formula like the last one. We're looking for a formula with n in it. So I decided to do this example. What if I wanted to find the sum of the first 5 terms of the previous series? This list right here. Well, if I'm looking for 5 terms, this is the first term, this is the 5th term, and n is equal to 5. I need all of those to substitute in here. N is 5 if I'm doing 5 terms. First term, last term, or 5th term. Ran the calculation and it was 5. But what's nice about this is this problem wouldn't be any harder if I wanted to add up the first 100 terms. If I knew what the 100th term was, I just would have put that right here, and I would have changed that to 100, or changed that to 100. I mean, you know, the calculation wouldn't have been any harder, but obviously physically adding 100 things would be very tedious. So this is actually a pretty nice formula to have if you know you're adding an organized list of numbers. So they ask us to do that. All right. And that's 10.2. So didn't really, 10.2 went pretty quickly. Because we're narrowly focusing what our list is like in 10.2. And I could skip on to I'm not going to do a separate video for this because I think it's very important that we learn 10.3 along with 10.2 kind of at the same time so we can compare them. So if 10.2 is based on adding the same number from step to step, 10.3 is based on multiplying. So if you look right here, I started with a 3 and I multiplied by 2. Then I multiplied by 2 again, and multiplied by 2 again, multiplied by 2 again. So the multiplying 2, same thing every time. It's called the common ratio. Multiplying by 2 every time is common, right? So how would we describe this list? It's a geometric series. So all series have a first term. It's 3 in this case. And if we say R, we're talking about the common ratio. And R, it means we're multiplying. Remember, D meant we were adding. R means we're multiplying. So the book is, I don't know, math is the formulas are very nice for something like this. The formula for this list is a sub n equals a r to the n minus 1. So if I just substitute those in, r is the first term. Sorry, a is the first term, r is 2. That would be the answer. And you could leave that as the answer. There's nothing wrong with, you don't need to try to simplify it or work with it. That's the answer. So this would be fairly hard to see on your own, just staring at this and say, what formula, when I put in a 5, gives me a 48, and when I put in a 4, because that's the 4th term, gives me a 24, and when I put in a 3, gives me, if we were trying to do what we're doing in 10.1, might be kind of tricky, but by the time we get to 10.3, it's just substitution into one of the easiest formulas we have in the whole book. A sub n equals a r to the n minus 1. I mean, there's just 1, 2, 3, 4, 5 characters. Pretty simple formula. All right. So that finds us that. All right, what else do we do? Well, we already know this. In addition to describing a geometric series with its A and its R number, in addition to describing it with a list, and describing it with a formula, we might be asked to find the sum of the first n terms. So what I was saying is, I feel like we should think of this kind of the same way we think of previous section. All right. Yes, we can calculate with the sum of the first n terms. All right. So here's the formula. S sub n, a 1 minus r to the n over 1 minus r. And I just want to remind you, if the formula has r in it, r means that's the multiplier from one step to the next. Substitute for the previous problem, and it left the screen, but let me write it down here in its new form. I have 3, 6, 12, 24, 48. What I want to do is find 3 plus 6 plus 12 plus 24 plus 48. And I can do that using this formula instead of just adding them up. By the way, just adding them up is pretty easy. Like, you know, you could pick and choose here. That's 60. That's another 30. I'm not going to try to do it, but you can do that. But this formula could add, as we're going to see, any number of terms, any number. So not just 5. It could add 1,000,000 terms, I suppose. All right, but S sub 5 to add 5 terms. And I'm just going to do my substitutions. First term, R, substitutes twice, N, because there are 5 terms, N. And 2 to the 5th is 32, so that turns out to be what? Negative 3, or 3 times negative 31 over negative 1. Negatives cancel. Yeah, I get 93, which I'm sure is the same answer I'd get if I added them together the, grade school way. Right. Now, I said you'd add these together even if there's 100 or whatever number. You just have to step up these numbers. They get very big very quickly, but you could do that. But there's something that we have in 10.3 that we don't have in 10.2. And I just got to tell you, this has racked the brains of students, not just students, but professional mathematicians, philosophers for, well, hundreds of years, actually. Philosophers had trouble with this idea, but it's been proven, and I mean, by every child who's ever held a calculator, in a way, that if r is between -1 and +1, we also can talk about S sub infinity, meaning the sum of not the first n terms, but the sum of an infinite number of terms. And like I say, if I put it that way, it sounds kind of harsh. It sounds hard to believe. Like, how can you add an infinite number of terms? So I picked an example. By the way, this is the formula. It's again, one of the briefest formulas. 1, 2, 3, 4 characters, including the minus sign. It's a very short formula. But this is the formula for adding an infinite number of terms if the conditions are right. The conditions are, it has to be geometric, meaning the list has to be based on multiplying to go from one term to the next. R has to be less than 1. Well, actually, we say the absolute value of R has to be less than 1 to be technically correct, but R has to be less. It can be positive or it can be negative, but R has to be between -1 and 1. And then we can add an infinite number of terms. So I picked this series because I made a claim earlier. You've seen this. Everyone has when they owned a calculator, the first calculator. All right. It didn't look like this, but I'm calling this S, or S sub infinity, and it's S sub infinity. I'm putting the ... here to indicate this thing goes on forever. 0.3, plus 0.03, plus 0.003. All right, so this is our first practical application where I'm just giving you the list, and I'm expecting you to tell me what A and R. All right? A is the first term, so that's visible. A is just what you see. So there's A. What's R? Well, R is the thing we're multiplying by every time. And if you look at what's going on here, yeah, I get 3/10, 3/100, 3/1000. And if you remember how multiplying decimals works, what you were doing is we're multiplying by 1/10 or 0.1. That by multiplying by 0.1, we can describe this other ways, but if we're forced to ask, what are we multiplying by? What will we multiply on a calculator to get from here to here? I think you can crack that code and figure out that it's 0.1. We have everything we need to substitute into this formula. S equals A, 1 minus R, so it's 0.31. What that says, that's a minus 0.1. I guess it looks fine. All right. 0.3 over 0.9, which if you multiply top and bottom by 10, which you can do with fractions, multiply top and bottom, you get 3 over 9, which is 1/3. So if I added this infinite list up, I'd get 1/3. Now, here's where I want to make a connection. At some point in your life, you learned that 1/3 was 0.33333, repeating. What does that mean? Well, it means that we're adding 0.3 plus 0.03 plus 0.003. Each one of these is a place value in this list. So if at some point somebody, you ever asked, why is 1/3 0.333 repeating? Why does it go on forever? We've kind of asked the other side of that question. Why is 0.333 repeating equal to 1/3? Well, we can take this list and prove essentially that it's 1/3 by using this formula and our understanding of geometric series. All right, this video, it is one of my, I guess, longer videos. I don't like making them too long for this type of thing because I still say videos like this do not put points in your test. You need to do problems to put points in your test. But in other words, if you had a problem like this, find the S sub infinity or add up this infinite list, the answer is 1/3. You got to put the formula in and figure it out. So calculations, doing the homework puts points in your test. There is another section of chapter 10, and that's 10.4, the binomial theorem, like a plus b to the n. We've already covered that, and there's really not much new there, so use what we were doing before. And I think that's it. I think that is 10.2 and 3. All right, so that's chapter 10, or what we're going to cover in chapter 10. And we'll see you in the next video.